So this is what we are going to be focusing on for the first part of this class, module 1, is how does an airfoil generate lift, which is really the single most useful thing we have invented, right, to control and manipulate air and have air to work for us. So lift from an airfoil. I'm just going to first of all give you a very broad outline of how would we interpret or explain the lift on the airfoil. And once we can interpret and explain the lift on the airfoil, we can start to predict what kind of a lift we generate from an airfoil, and how do we change the shape of an airfoil to generate the kind of lift we want. Okay, so as I have said a little bit earlier, the lift from an airfoil is generated by the pressure difference between the upper surface and the lower surface. So the next logical question is, why is there a pressure difference between the upper and lower surfaces? And that's really how we dive into the dynamics and the kinematics of fluid flow. And to simplify everything else, right, to simplify the elements that are not essential for explaining the generation of lift, we make these assumptions we have in module 1. Okay, the assumptions are, first of all, the streamlines, right, as you see over here, the streamlines, they always attach the surface of the airfoil, both on the upper surface and on the lower surface. So if you trace another streamline on the lower surface, you're going to see pretty much the streamline is always going to attach to the surface of the airfoil without going anywhere else. Okay, this assumption, as we're going to see starting in module 2, is the implicit assumption. If you start to look at viscosity, right, you're going to see, okay, the streamline on the surface is actually doing something a little bit more subtle than attaching just on the surface. And you're going to start to see the possibility that at higher angles of attack, the streamline is actually going to separate wildly from the surface of the airfoil. So this is assumption number 1. That's our implicit assumption. The consequence of the assumption is really that the streamline attaches to the airfoil. Assumption number 2 is the incompressible assumption. As I have introduced earlier, the incompressible assumption is not really about the air, the property of the fluid, about air, because we all know that air is compressible. The incompressible assumption really has to do with the pressure field. The consequence of the incompressible assumption is that the pressure field is going to do whatever it takes to make the streamline attach to the surface of the airfoil, right? Our assumption number 1, implicit, is that the streamline is going to follow the surface of the airfoil. Assumption number 2, the incompressible, is basically saying that the pressure field is going to act in order to enforce assumption number 1. Now let's take a deeper look at what that assumption tells us. Okay, we all know Newton's second law, right? So in order to generate an acceleration, we must have a force. And now let's take a look at what kind of acceleration do we have on the surface of the airfoil. So now let's just take a look at a fluid element over here. Look at the red dot I just draw. Which direction is the fluid moving? Well, we all assume this is a steady state flow field, right? So the element is just following the streamline. So this element is moving towards the right, following the streamline. So that's the velocity of the particle over here. Now, in order to start using Newton's laws, it's important not only to use the velocity, but also the acceleration, right? F equal to ma. So what is the acceleration of this particle over here? Now that's a little more subtle. Let's look at what the particle is doing 1 moment later. So let's change the color to green. So a moment later, the particle follows downstream. Actually, green doesn't look very good. Let's change to blue. A little bit later, the particle is now over here, and the velocity again is following the streamline like that. Acceleration deals with the change in velocity. So what's the difference between the blue arrow, the blue velocity at a moment later, compared to the pink velocity a moment earlier? What's the difference in the two vectors I have drawn? Well, let's use a white arrow to emphasize the difference, right? So let's, first of all, let's move the pink arrow, translate it to the location of the blue arrow. And then let's look at the difference. Let's use yellow to draw the difference. The difference is the difference between the pink arrow and the blue arrow. So let's just draw it a little bit more precisely. It's downward. The acceleration is downward. It's obvious when you think of this fluid particle turning, right? It's turning downward. It's following the streamline, and the streamline follows the surface. The surface has a curvature, so the particle moves along the path with a curvature. So, of course, the acceleration is called the concentric acceleration, right? It goes towards the direction of the curvature. This is all kinematics, right? So this is basically looking at the kind of a fluid motion, as we're going to be starting to look at. Kinematics is to look at a flow field and figure out what is the velocity and ultimately what is acceleration. What is the acceleration of the fluid particle? And of course, once you have that, you have F equal to ma. So there has to be a force, some kind of force that makes the fluid particle accelerate downwards. And this force is pressure, right? This is the pressure force. And we all know that the pressure exerts a force that makes the particle accelerate towards the direction of lower pressure. Right? You have a higher pressure and you have a lower pressure somewhere else. And the difference in the pressure always drives the fluids to accelerate towards the lower pressure region. So then you know that when the streamline curves downwards, you have different pressure. You have higher pressure regions upward, and you have low pressure regions downward. So it's the difference, it's the gradient or a spatial difference in pressure that drives the flow to curve along the airfoil. And now assume that very far away from the airfoil, the pressure is the same as free stream. You are going to be knowing that on the surface, when there is a curvature, the pressure is lower than the pressure in the free stream. Okay, so this is a qualitative explanation of why on the upper surface of the airfoil, the pressure is low. It creates a lift by suction. Of course, you're going to say, okay, on the lower surface, there is a similar curvature, and it's also going to make the pressure lower than the free stream. And you would be correct. The difference between the upper surface and lower surface is quantitative, not qualitative, right? On both lower and upper surface, the pressure is likely lower than the free stream, but the difference makes the lift. And that's why we need a quantitative analysis starting from the next lecture. So starting from the kinematics, we have the dynamics. That's where the aerodynamics comes in, right? It's essentially looking at what are the forces that makes the flow go the way it does. Okay, so the dynamics is with what is F, right? F, for example, in this case, F equal to minus the gradient of pressure. So this sign is the nabla sign is the gradient. Okay, so this is the gradient divided by the density. So sorry, this is pressure divided by the density of the well, this is actually acceleration. So the pressure force is just the negative of the gradient of the pressure, right? So that's the force. So this is dynamics. And starting from the next lecture, we are first going to look at the kinematics and figure out how does the fluid moves and accelerates. And then we look at the dynamics of what is causing the flow to move the way it is. And combining them, we're going to be explaining qualitatively and quantitatively how airfoils and wings generate lift.